the standard states in North America. But you have to be warned that in Europe, for example, they are not the same. But anyway, we're going to use what we use over here. So let's define our standard states. The truth of that is the recognition of the fact that it is arbitrary. We have this choice to make. All right, we have different cases. So let's look for gas phase components. Either pure or in a mixture. The standard state is the pure hypothetical ideal gas. At the temperature of the system, so I'm just saying at T, and the standard pressure is, let's call it a P standard, is equal to 1 bar. So this is where it's different. In Europe, they let the standard state pressure be the pressure of the system. But in North America, we set it at 1 bar. Now, in the older literature, you'll find it at 1 atmosphere. But if that's the situation, you have an old database, you might need to do some conversions. But let's, for now, not worry about that. The standard state pressure is rigorously set at 1 bar. So the fugacity of a component in a standard state is going to be equal to the fugacity of the hypothetical pure ideal gas. But since it's an ideal gas, that's the pressure, and we set it equal to 1 bar. Whoops. So the fugacity in the standard state is equal to 1 bar. What I'm going to do here is run through the definition of the standard states for the different situations that might be encountered, and then we'll go back and develop expressions for the activities. So for a liquid or solid component, and this is either pure or in solution. Standard state is equal to the pure liquid or solid at T, and the pressure equal to 1 bar. So standard state would be equal to, using 0 here to indicate pure, it's 1 bar. Those are the main ones that we're going to actually encounter as we go forward here, but let's finish off the list here by looking at for a solute component in a dilute solution. So what this is a component in a hypothetical, then we could abbreviate it that way, Henry's law solution. At either x2 goes to 1 or the molality goes to 1 molal. The values for those standard state fugacities are then the respective Henry's coefficients. So that's the whole story. There really is nothing else. So these are the definitions that we have for the standard states. The next issue then is to look at the evaluation of the activities for each of these. In these different situations. So now let's delineate pure gases. Nope, then there's no hat. And the definition of activity is the fugacity of whatever it is over the fugacity in the standard state. So what is the fugacity? How do we write the fugacity of a pure gas? It's the fugacity coefficient times pressure. And what we've got down here for the fugacity of our standard state is the thing that we call P0, but we set that equal to 1 bar. So I can write that simply as VIP. Now, something you have to remember when we write that out. Looks odd because we know that activity is dimensionless. But this looks like it has dimensions of pressure, but it doesn't because we've got that P0 equal to 1 bar in the denominator. So this is dimensionless, but the understanding is that P must be in units of bars for that to be right. And we have assumed here that P0, our standard state pressure, is equal to 1 bar. So that makes this the correct expression for the activity of a pure gas. Gas component in a mixture. Yeah, we need to write the hat. It's Fi hat over Fi standard state. Well, now remember how we write that out. That's Yi Vi hat P, and this is now our P0, which is just equal to 1. So this gives me Yi Vi hat P. There's the activity of a component in a gas phase mixture, again with the same understanding. The pressure here has to be in units of bar, and our P0 has been set equal to 1 bar. That has to be understood. The next item in our list would be a pure condensed phase, so pure liquid or solid. The activity would be equal again here, the fugacity here of that pure liquid or solid, so I'll write it that way. And our standard state here again is going to be just this fugacity here of the pure liquid or solid at P0 equals 1 bar. So if I write this out, what I see, this is the fugacity of the pure material at P. This is the fugacity of the material at 1 bar. So how do we express that difference? That's gonna be exponential here, that's our pointing vector. This P0 is gonna be, whoops, I should put the 0 up high. And we take that as essentially 1 unless we're dealing at high pressure. So for purposes, our purposes, we take the fugacity of a pure liquid or solid is simply equal to 1. So for a component in a solution, again, we've got Fi, what is that going to be? Over Fi standard state. We write this out as gamma I xi Fi 0, but this is now at P. And here I've got Fi 0 at P0. So what I end up with is gamma I xi times the pointing factor P0 being just R1, and this is, for all practical purposes, just gamma I xi. So there's the activity of a component in a solution. It's just the activity coefficient times the mole fraction. So for a component in a dilute solution, let's call that A2 is equal to, whoops, now the way we write that out with complete generality in a dilute solution, let's do it assuming we're doing it in terms of mole fraction. That's gamma 2H times x2 times Henry's constant. But the fugacity in the standard state is, if I could write it right, it's Henry's constant, so these cancel out and I get gamma 2H times x2. Or I could have gamma 2HM times M2. So it could be either of those things. So here you have it, the complete list of the standard states, the definitions of the standard states, how we calculate the fugacities in the standard states, and then ultimately the activities in the standard states. And here I have it all summarized here for us, because now we can, I posted this, so you could have that for a reference, and there's where we will go to calculate, to implement our statement of the equilibrium criteria, which if we go back, what we remember is that our equilibrium criterion was that G of reaction this thing is equal to 0. Now I can plug in for these mu i's. And now, since you notice that what I've dealt with, with the exception of the Henry's law cases, that the standard states are pure components. So I will then now make myself consistent with the notation in the textbook and use for the standard state the 0, because they are in fact pure components. So this is equal to mu 0 plus RT logarithm of the appropriate activity, whatever that's going to be. Now what we can do is then take every one of these, plug it in up here, and get an expression for this total molar Gibbs free energy change of reaction in terms of the activities, which we can relate back to composition. Well, we're out of time now, but I'm going to finish this up then on Friday, and we'll move on then. Now, once again, for those that came a bit late, there's going to be no quiz on Friday. It's going to be a regular lecture. I've signed a value 25 for every one of you for quiz 4. So